Welcome to the lecture series on CFD, Part 1. This is lecture 15 on application examples for solving unsteady scalar transport problems. In this lecture, we shall analyze the performance of some of the time integration methods described in the two previous lectures on two test cases. The first test case is the unsteady version of the one-dimensional problem studied in lecture 6 with one difference. Now, one of the boundary values varies sinusoidally in time. Although of little practical relevance, the test case is still useful for testing the features of time integration methods. Iteration errors are minimized to round-off level because we have an efficient direct solver for one-dimensional problem, the TDMA algorithm described in lecture 10. 9 schemes were implemented in the test code, which is available in supplementary material for this lecture. First order explicit and implicit Euler methods, second order Crank-Nicolson, quadratic backward, Adams-Bashforth and Runge-Kutta methods, and fourth order Adams-Bashforth, Adams-Moulton and Runge-Kutta methods. The second test case is the unsteady version of the test case studied in lecture 9. Here only first and second order methods are analyzed. Only the transport equation for a scalar variable is solved. The velocity field is prescribed analytically and is steady. The initial condition is a zero scalar field, while a linear variation of the scalar variable is prescribed on one boundary, and we are observing the propagation of the boundary influence into the field due to both convection and diffusion transport. In this slide, the one-dimensional test case is defined. The solution domain is 1 meter long and subdivided into 80 equal segments by a uniform grid. Finite difference method is used for discretization. Thus, we have two boundary nodes and 79 inner nodes at which the solution is to be computed at each time step. We are solving the one-dimensional version of the scalar transport equation in differential form without source terms. The convection term is moved to the right-hand side so that the equation looks like the ordinary differential equation. Density, diffusion coefficient, and velocity in x direction are all set to unity. Central differences we use to discretize both convection and diffusion terms. The variable phi is held constant at phi equals 0 at the left boundary, while it starts varying sinusoidally at the right boundary at t equals 0.05 seconds. Until then, both boundary values are equal to 0. This is intended to provide enough past data for methods which use information from several previous time levels. We are monitoring the value of phi at x equals 0.75 meters over time. Temporal discretization errors are determined by assessing the variation of this value at t equals 0.4 seconds as a function of the time step size. The dimensionless parameters d and c are also observed. Because of diffusion, the parameter d is of primary importance because it strongly affects the stability of explicit and semi-explicit methods. This figure shows the variation of phi between west and east boundary at 4 time instants: 0.2, 0.4, 0.6 and 0.8 seconds after the start of simulation. At t equals 0.6 seconds, the right boundary value is reducing and the maximum value is found inside solution domain. The oscillation period is 0.6283 seconds, as can be seen in the plot on the right, which shows the variation of phi at x equals 0.75 meters over time. The effect of the initial condition, zero values everywhere, is seen only in the first period. Later, the solution is fully periodic. Most explicit methods are unstable until the dimensionless parameter d becomes smaller than or equal to 0.5. This is here the case for the explicit Euler, labeled EE, fourth order Adams-Moulton, labeled AM4, and both second and fourth order Runge-Kutta methods, labeled RK2 and RK4 respectively. Adams-Bashforth methods require smaller time steps. The second order version, labeled AB2, is still unstable at d equals 0.5, while the fourth order version, labeled AB4, is unstable up to d equals 0.125. Implicit methods, implicit Euler, Crank-Nicolson and quadratic backward scheme are stable at all time steps. For lower values of diffusion coefficient gamma, explicit methods are stable at larger time steps. D is the critical parameter and it decreases at the same rate as gamma decreases. Note that for the same time step, D increases by a factor of 4 when the grid spacing is halved, so the stability limit moves to a 4 times smaller time step. These two figures show how sensitive the explicit schemes react when the stability limit is only slightly exceeded. For D equals 0.4992, both the first order explicit Euler and the second order Runge-Kutta method produce a smooth solution. When the time step is only slightly increased so that D becomes greater than 0.5, here 0.5024, the solution process diverges. In the case of explicit Euler scheme, oscillations start developing around t equals 0.22 seconds, leading to a rapid divergence as t increases above 0.25 seconds. The values from consecutive time steps oscillate alternately around the correct solution. In the case of second order Runge-Kutta scheme, no oscillations are produced like with explicit Euler scheme. The computed values tend smoothly but rapidly toward minus infinity for t greater than 0.2. Black lines at t equals 0.3 seconds show the difference in accuracy. First order scheme predicts the value of phi below 0.8, while the second order scheme predicts the value greater than 0.8. To see how the solution changes with reducing time step size, these two figures show the variation of phi at x equals 0.75 meters with time around the first peak. See slide 5 for the variation over 3 periods. Zooming in was necessary because the differences between solutions obtained with different time steps are very small for second and higher order schemes. The left figure shows the results obtained with the first order implicit Euler scheme. It is stable even for very large time steps. So curves are shown for 7 time steps. One can clearly recognize the typical feature of first-order schemes. The difference between solutions obtained with 2 consecutive time steps in a series with step halving is also halved. According to Richardson extrapolation, the error in the solution obtained with the smallest time step is equal to the difference between that solution and the solution obtained with a twice larger time step. We see from this figure that Crank-Nicolson scheme is much more accurate than the implicit Euler scheme. The curves for the 4 smallest time steps fall practically on top of each other and cannot be visually distinguished in the plot. Only for the first 3 largest time steps, one can see that the difference in solutions reduces by a factor of 4 when the time step is halved, as expected of a second order method. This figure shows the same information as the figures from previous slide, here for the quadratic backward scheme. It is also a second order method, but the errors with the largest time step are visibly larger than in the case of Crank-Nicolson method. The curves for the 3 finest time steps cannot be distinguished from each other in the plot. The figure on the right shows the profiles obtained with different schemes and fine enough time steps, showing that all methods lead to the same solution as required. These plots show how the value of phi at x equals 0.75 and t equals 0.4 seconds varies as a function of time step size when computed with different time steps and integration methods. The figure on the left shows the convergence with time step refinement for the 3 implicit methods that are stable also for very large time steps. The quadratic backward scheme leads to larger errors at large time steps than the Crank-Nicolson scheme, but they both quickly converge. The first order implicit Euler method needs much smaller time steps to converge. The figure on the right shows the zoom into this range of values. Added are also the results from explicit schemes which are stable in this range of time steps. The results from second order schemes cannot be distinguished from each other. while the two first-order methods approach the time-step-independent solution from opposite sides and can be well distinguished from each other even for the smallest time step. Results from fourth-order schemes do not vary on the 12 most significant digits. They become stable at very small time steps when the solution is already more accurate than necessary for most practical applications. Because of a high value of diffusion coefficient, the parameter d becomes small enough for explicit schemes to become stable only for time steps below 0.1 milliseconds. At so small time steps, temporal discretization errors from second and higher order schemes are much smaller than needed. Implicit schemes can use very large time steps, and the only criterion for the choice of time step is the desired accuracy. Richardson extrapolation from all four second-order schemes gives the same value for the time-step independent solution at 12 most significant digits. Temporal discretization errors for each scheme and time step are determined by subtracting the computing value from this estimate of the exact value. This figure shows the absolute errors for all first and second-order methods tested. Errors could not be reliably estimated for fourth-order methods because of interference with round-off errors. If the aim is to have errors around 0.1%, this can be achieved with implicit second-order schemes with time steps which are 2 orders of magnitude larger than the stability limit of explicit methods. Explicit methods are thus not suitable for problems dominated by diffusion, especially if small grid spacing is required, for example, to resolve the boundary layer at walls, because of this dependence on grid spacing. For the same grid, 100 times lower gamma leads to 100 times lower value of d, so 100 times larger time steps can be used with explicit methods. This is demonstrated in the next slide, where results with gamma equals 0.01 are presented. For gamma equals 0.01, d becomes 100 times smaller than values indicated in the table in slide 6. Therefore, explicit schemes become stable at 100 times larger time steps, which makes it possible to estimate the temporal discretization errors also for fourth-order schemes. This figure shows the value of phi at x equals 0.5 and t equals 0.4 as a function of time step size, computed with explicit Euler, second-order Runge-Kutta, fourth-order Runge-Kutta, and fourth-order Adams-Moulton schemes. The results from the two fourth-order schemes cannot be distinguished in this plot. Richardson extrapolation from both second and fourth-order Runge-Kutta schemes gives the same value for the time-step-independent solution at 9 most significant digits. Temporal discretization errors for each scheme and time step are determined by subtracting the computed value from this estimate of the exact value. This figure shows the error in percentage of the reference value for the implicit Euler and second and fourth-order Runge-Kutta methods. When the time step is reduced by 1 order of magnitude, errors are reduced by 1 order of magnitude for the explicit Euler scheme, 2 orders of magnitude for the second-order Runge-Kutta method, and 4 orders of magnitude for the fourth-order Runge-Kutta scheme, as expected. If the aim is to have errors around 0.01%, this is achieved with the second-order Runge-Kutta method with the largest time step for which it is stable. The fourth-order scheme is too accurate for this problem already with the largest time step which guarantees the stability. This slide shows the definition of the two-dimensional test case. It is the unsteady version of the problem studied in lecture 9. We are solving this transport equation for a generic scalar phi on a square solution domain with these fluid properties. The velocity field is prescribed analytically and is steady, u equal x and v equal minus y. It corresponds to the inviscid stagnation point flow. The initial condition is 0 values of phi in the whole solution domain. 0 values are also specified at the inlet boundary. At the west boundary, phi varies linearly as shown here. South boundary is the symmetry plane, and at outlet, zero gradient of phi in x direction is prescribed. Finite volume method is used for space discretization, and central difference approximations are used for both convection and diffusion fluxes. In addition to the research code, the SimCenter Stasisian Plus software from Siemens was also used. To judge the time step dependence of solution, we are monitoring the flux of phi through the west boundary at t equals 0.12 seconds. This plot shows the uniform 80 by 80 control volumes grid used in both codes. This plot shows the prescribed frozen velocity field corresponding to the invested stagnation point flow. Streamlines are indicated by the line integral convolution method, and the color represents the velocity magnitude. Pressure is not computed, but its isolines are circles, like for velocity magnitude. Here we see the animation of the variation of phi in the whole solution domain over 2 seconds from the start of simulation. If phi is assumed to be temperature, we see how the cold fluid coming from inlet is gradually heated up by the hot wall. As the time goes on, the scalar propagates further across the flow, leading eventually to a steady state, because neither boundary conditions nor the velocity field change in time. The animation was created from a simulation with SimCenter Stasisian Plus software using the fully implicit second-order quadratic backward time integration scheme, second-order linear upwind scheme for convection fluxes, and the default discretization for diffusion fluxes, which is approximately equivalent to central differences. This plot shows the variation of flux of phi through the west boundary as a function of time for the explicit Euler scheme and 2 time steps. Initially, the solution is smooth for both time steps, but for the slightly larger time step, oscillations around the correct solution start developing after some time with exponential growth and divergence. Interestingly, oscillations start at a lower value of the parameter d than expected. The stability limit for this scheme is typically d equals 0.5. See slide 7 for 1D case. Here, the solution is smooth at d equals 0.2, red line, while for d equals 0.213, black line, it becomes oscillatory and diverges. These 2 figures show the variation of the flux of phi through the west boundary as a function of time for the Crank-Nicolson scheme and different time steps. Initially, oscillations are present until the parameter d drops below 0.5. The oscillations are decaying with time, contrary to explicit Euler scheme where they grow exponentially. As the time step is reduced, the amplitude of oscillations is also reduced, as well as the time before the oscillations die out. The left figure shows the zoom until t equals 0.12 seconds, while the right figure shows the variation until t equals 0.6 seconds. The time until oscillations die out reduces by a factor of 4 when the time step is halved. The left figure shows that at t equals 0.12 seconds, solutions for the 2 largest time steps is affected by the oscillations. With smaller time steps, oscillations die out earlier. In slides 19 and 20 of lecture 13, one can see that the coefficient multiplying the value of phi at cell center from previous time step can become negative for large values of the parameter d. In a 2-dimensional case, this coefficient equals to 1 plus AE plus AW plus AS plus AN. The contribution from convection cancels partially out when central difference approximation is used. It cancels completely on a uniform flow field. And the contribution from diffusion is minus d half. Thus, 4 times d half gives minus 1 if d equals 0.5. And for values of d greater than 0.5, the coefficient of phi p from time level Tn becomes negative. This is what causes the oscillations. As phi grows in the wall vicinity, the contributions from neighbor nodes lead to oscillations dying out. These 2 figures show the variation of flux of phi through the west boundary as a function of time for the implicit Euler scheme on the left and for the quadratic backward scheme on the right, using different time steps. A monotone first-order convergence is obvious in the case of implicit Euler scheme. The quadratic backward scheme produces some undershoots at large time steps, but as the time step is reduced, the lines converge to the red line representing the smallest time step and a very accurate solution. This figure shows the flux of phi through west boundary at t equals 0.12 seconds computed with different time integration schemes and time step sizes. The Crank-Nicolson scheme has problems with oscillations at large time steps, as shown in slide 17, but later the results are almost the same as from quadratic backward scheme. Richardson extrapolation from values obtained with the two finest time steps in Crank-Nicolson and quadratic backward scheme gives the same value at 9 most significant digits. This value is used as the reference to compute temporal discretization errors for each scheme and time step size. This figure shows the variation of temporal discretization errors with time step size. Both Euler schemes show the slope 1, as expected of first order methods, while the other two schemes show second order convergence. Reduction of errors by 2 orders of magnitude when the time step size is reduced by 1 order of magnitude. The explicit version is only stable at small time steps. It approaches the exact solution from the opposite side, but the absolute errors are of the same magnitude as for the implicit version. If the aim is to have errors around 0.01%, this is achieved with second order schemes at moderate time steps, while the Euler scheme would require 2 orders of magnitude smaller time step. This figure shows the comparison of results obtained with the finite volume based research code available in source form in supplementary materials for lecture 15 and with the commercial software SimCenter STASIS from Siemens, also based on finite volume method. In the research code, central differences were used for both convection and diffusion, while in SimCenter STASIS second order linear upwind scheme was used for convection and central differences for diffusion. The same uniform grid with 80 by 80 cells is used. In SimCenter STASIS transport equation for a passive scale is solved on a frozen velocity field defined using an analytical field function u equal x and v equal minus y. The figure shows the flux of phi through the west boundary at t equals 0.12 seconds computed with 2 integration schemes and various time steps. IE denotes the first order implicit Euler scheme and QB denotes the second order quadratic backward scheme. The curves from 2 chords for both schemes cannot be distinguished in the plot. They fall almost perfectly on top of each other. Let me briefly summarize the main takeaways from this lecture. Explicit methods of all orders suffer from severe stability-imposed limits on usable time step sizes when diffusion is significant and grids are fine. At time steps for which the schemes are stable, the errors are already much smaller than is in most practical applications necessary. Higher order explicit schemes are useful when the flow is highly transient and very small time steps are required for accuracy reasons. For example, when studying explosion or implosion-like phenomena, for example, growth and collapse of cavitation bubbles. The only 2 methods that do not suffer from stability issues are the fully implicit schemes, first order implicit Euler and second order quadratic backward. This is why all commercial codes offer these 2 schemes. The first order implicit Euler scheme is useful when computing flows that are weakly transient or tending to a steady state. The second order quadratic backward scheme is recommended for time accurate simulations at practically no extra cost.